Welcome back. We have a great show for you today. Well, you might not think it's so great. Very difficult stuff. Today we're going to cover algebraic manipulations of trigonometry identities. Now that's quite a mouthful, and that's quite a lot, because to do that, you have to know basically in your head, all of your algebra and all of your trigonometry, which if all of you all know all that, you'll be the first student that I've had that does. So basically today is a huge review session. So I'm going to go pretty fast because I'm dreaming in my mind that you know all this. Okay? So with that said, let's go. Okay? What's that? The camera people want me to do some of last night's homework. Okay? So let's do that. We'll do some homework examples real quick because we don't have much time, and then we'll do it. Okay? Remember last time we were supposed to sketch graphs of sine and cosine functions. Okay? Well, one of the ones in the homework was y equals 1/2 sine of 1x. Okay? Well, the first thing you're asked to do is find the amplitude, which remember that's the number in front of the sine, so that's a half. Okay? The frequency, which is the frequency, how often you get the spaghetti curve over a 2 pi distance. And in that case, it's 1. It's the number in front of x. And the period then is 1 over that number times 2 pi. That's the length of your spaghetti curve, if you would. And one other thing we're going to need to know is the phase shift. The phase shift is always minus c over b. And in this case, we don't have a c, so that's 0. So we're going to end up with a phase shift of nothing. Okay? So let's see what it's going to look like. First thing I do when I sketch these things is I find out where it's going to begin. Now there's no phase shift, so it's going to start right at the origin. Okay? And then I figure out where it's going to end. Okay? Now this one's going to have a period of 2 pi, so it's going to end up at 2 pi. Okay? So I've got to do one spaghetti curve's got to begin there and end at 2 pi. Okay, now how tall is this bad boy going to be? It's going to have an amplitude of 0.5, so it's not very tall. Okay, so let me start and finish there and do an amplitude of 0.5 for one spaghetti. Ready? Say it with me. Spaghetti. Oops, it's a sine curve, so we're going to start at the 0 point. Spaghetti. Let me go backward. Spaghetti. And I think I got a little sp in there. There we go. Okay? So that's basically what your picture should look like. It should start right at the origin. And you do have the sine curve, which does look like an S if you're laying down. Okay, then we'll quickly do another one. Okay, now this one I want to do because it's a cosine. Okay, what's the amplitude of this thing? Let's see, it's going to be the 1/3. The frequency over 2 pi is the number in front of x. Once again, this is a pretty easy one, is 1. The period is going to be 1 over that number times 2 pi, which is 2 pi. And then the phase shift, once again, we have no phase shift. Okay, let's see. We're going to start off, since there's no phase shift, we'll start off right there at the origin. Not really at the origin because it's a cosine, okay, but basically at 0, if you would. Okay, and we're going to end again at 2 pi. Now our amplitude is only going to go as high as 0.33, or 1/3. It's a little bit different here in that since it's the cosine, we're going to start at its highest point, which in this case is 0.33. And we're going to draw a cosine curve. Remember the cosine starts with a C. It almost looks like a C. And I like to say cuckoo with that. Okay? Cuckoo. Let's go the other way. Cuckoo. Okay, I don't think I have another one for that one. So that's that one. Okay? I'm going to do one more. I'm going to do the hardest one that was on the homework. Okay? Ugh, look at this bad boy. Okay, it's got everything. It's got phase shift. It's got the whole schmagooga. Okay, the amplitude is 4, just like the other one's, the number in front of sine. The frequency over 2 pi is the 1/4, the number in front of x. Now the period is going to be 1 over a 4th. Let's see, what's 1 over a 4th is 4, times 2 pi is 8 pi. So the period, it's going to take 8 pi for this thing to get the full ride. Okay, and then the phase shift is minus c over b minus pi over 8, divided by 1/4, which ends up being minus pi over 2. So we have to move pi over 2 to the left, if you would. Okay, let's take a look at it. Let's see. It's going to start here, minus pi over 2. I have it marked off in pi units. Okay, now it's going to end up all the way over here, 8 pi away. Now I'm not quite to the 8 pi because I've moved over half a pi, you see. Okay? Now, how high am I going to go on this? I'm going to go up all the way up to 4, because that's the amplitude. And what is this? This is the sine. Okay, so I got to do an S. Ready? Spaghetti. Let's go the other way. Spaghetti. Well, now let's review doing it with a calculator. Okay? Before I do it, because I'm going to do it first, I just want to point out some of the tougher buttons that, I mean, we've done them before, but you know, only once. And that is, don't forget the pi button. Okay? You had to, you know, use that on your homework. And the way to get the pi button is you're going to have to do the second button first. So you do second, then pi. Okay? Okay, let me try this thing. Let's see, I'll turn my calculator on. You get yours while I'm doing this. Okay? Okay, let's see. The first thing I want to do is make sure that I'm in radian measure, because I see pi there, I don't see degrees. Now, if I don't see degrees, I know I'm in radian measure. I don't know the calculator knows that, though. So I'm going to hit mode, and son of a gun, I am in degree mode. So let me go down and make sure I'm in radian, hit enter, okay, and then I'll clear out. Okay, I'm safe now. Now I'm going to hit y equals. Okay, I got something from there before, so I'll clear it out. And I got to type this. This is a mouthful. 4 sine 1 divided by 4. Now I have to hit the X button. Remember that? Okay. Plus pi. Now how do I get pi? Second pi divided by 8. Now I need a right parentheses. Okay? Now I'll hit the graph button and see what I get. Well, I'm not real happy with this. Okay? As I can see, it's taken a long time to get there. I feel that I'm way too far out. So the solution to this, and it's the same solution for everything, whether you're too far out or too far in, is to hit the zoom button and to zoom to trig. So I can hit 7, but I'm going to cursor down so you can see what's happening, and hit enter. I'm going to zoom out a little bit. I'm not happy with that. Zoom. Zoom out. Okay. Now the reason I want to do this, you could do it on your homework, it's not the end all, is that I can check my sketch is okay, and I can see, at least from this point right here, that I'm a king. My sketch was right, because I remember it started at that point, so I'm in good shape. On the test, you'll mark these spots, whether they're pi over 2 or 3 pi or whatever they are. Okay? Now you try it. Let's see. You're going to hit mode, make sure you're in radian measure, okay, and then come out with your clear. Y equals, find that button. Type all this in. Holy, go to war. 4 sine 1/4 x plus, now get your pi. That'll be second pi divided by 8. Do your parentheses. Hit your graph button. Now, just in case you need to, hit zoom trig. Okay? You happy with it? Okay, you might zoom in or zoom out, but I think zoom trig is going to be a solution for you. Okay, let's clear out of there. Okay, so there's your review of your homework. Okay, now, we're going to have to review the trigonometry basics, and then we'll review the algebra basics. That's what today's about. Okay? Remember your trigonometry. Basically, you're supposed to know this is the hypotenuse. If x is the angle, then this is the opposite leg, and this is the adjacent leg. Okay? The tangent is the opposite over the adjacent. The sine is the opposite over the hypotenuse. You know all this. And the cosine is the adjacent over the hypotenuse. Okay? The cotangent is the adjacent over the opposite. The secant is the hypotenuse over the adjacent. And the cosecant is the hypotenuse over the opposite. You're saying I know all this? Good, because it's review. Okay? Now, in a negative angle, a negative acute angle, I'll say, in the fourth quadrant, we could go around this way, and it will be positive. But if I go backward in this direction, it's a negative angle. Okay? And the signs are going to change here. What's going to change? What's going to be critical? Let's see. That point in this quadrant is plus x and minus y. So the x part of this triangle is positive, whereas the y part is negative. Okay? And it is a right triangle, as you can see. So the sine, which is usually the opposite over the hypotenuse, in this case is going to be, because the hypotenuse is 1, it's going to be negative y over 1. So it shouldn't surprise you that for a negative angle, the sine is going to be negative. The cosine is still going to be positive. You can go positive, negative, doesn't matter. Why? Because in this quadrant, x is positive anyway. So you kind of relax with the cosine. And the tangent, which is usually y over x, is going to be, in this case, negative y over x. Okay? So if for a negative angle, it's going to affect the tangent and the sine, but not the cosine. Okay? So let's review that. The sine of a negative angle is the same as the negative sine of the angle, of the regular angle. Okay? The cosine of a negative angle is the same. You can take the negative away all you want with a cosine. It's going to be critical when we're doing simplifications. Okay? The tangent, we can't just take the negative away. We have to move it to the outside. Let's do the other three real quick. And I'm showing you why here. The cosecant, it involves the y. It's the hypotenuse over the y. So we're not going to be able to take the negative away there. We're going to have to bring it to the outside. The secant involves the x. It's the hypotenuse over the adjacent. So we can just take the negative away, much like the cosine. Okay? And the cotangent is the reciprocal of the tangent. We're going to have to leave the negative there. Okay? So, and you can see why, as I've shown you in each case. The ones that involve the y, which is negative for a negative angle, we're going to have to leave the negative there. Okay? Other things we'll review. I'm going pretty fast here. Okay? Consider, we just showed you that the tangent is the opposite. I kind of got the opposite on top there as red over blue there. Opposite over adjacent. The sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Okay? Quickly, the cotangent, now the red's in the bottom. The cotangent has the adjacent over the opposite, and the hypotenuse over the opposite, etc. Okay? So couldn't you say that the cosine is 1 over the secant? Okay? Because the cosine, for instance, being the adjacent over the hypotenuse, the secant is the hypotenuse over the adjacent. That's why the cosine is 1 over the secant. Another thing worthy of knowing is the sine is 1 over the cosecant. The tangent is 1 over the cotangent, or the reciprocal of it. Okay, we're going to need to remember the secant is 1 over the cosine, the cosecant is 1 over the sine, and the cotangent is 1 over the tangent. Okay, now the ones that you really care about are these ones, because later on today what we're going to try and do is get rid of the secant, cosecant, and cotangent. Okay, we're going to try and change everything basically into sines and cosines. Okay, so those are the ones we really want to remember. Okay? What else? There's some special things, I think this is new, about the tangent and the cotangent. Okay, consider that the tangent is the opposite over the adjacent. Okay, we know that. Big deal. If we divide the whole top by hypotenuse and the whole bottom by hypotenuse, the opposite over the hypotenuse over the adjacent over the hypotenuse, couldn't we say that the tangent is the same as the sine over the cosine? And it is. Okay, and that's going to be our way of getting rid of the tangent. We're going to change it into the sine over the cosine. Okay? Same deal with the cotangent, except he's the reciprocal. Okay, the cotangent, which is the adjacent over the hypotenuse, will play our little the adjacent over the opposite, play our little hypotenuse trick. Divide everybody. If you do it to everybody, it's okay. It's fair. Divide everybody by the hypotenuse. And then in the top, we'll have, what's in the top? The adjacent over the hypotenuse, known downtown as the cosine. And in the bottom, you have the opposite over the hypotenuse, which is the sine. So we could say that the cotangent, if we want to get rid of it, we could switch it into the cotangent's the same as the cosine over the sine. And we're going to be doing that later today. Okay? One more. Remember your old buddy, the Pythagorean theorem. For right triangles, a squared plus b squared equals c squared. Okay? A, b, and c. Couldn't we say, if this was the angle, that's the opposite, the adjacent, and the hypotenuse? So couldn't you say that the opposite squared, instead of a, we say opposite squared. Instead of b, we'll say adjacent squared. Instead of c, we'll say hypotenuse squared. Okay? Big deal. Wow, this is one of the basic identities, one of the most famous identities of all of trigonometry. If I take that equation and divide everybody, as long as I do it to everybody, it's fair. Okay? Divide everybody by the hypotenuse squared. Now, you'll never have to think of that. You know, a very smart person thought of this, Pythagoras, as a matter of fact. You divide everybody by the hypotenuse squared. What do we have here? The opposite over the hypotenuse squared, which is the sine. The adjacent over the hypotenuse, which is the cosine, or cosine squared. And the hypotenuse over the hypotenuse is 1, okay? So anytime you see sine squared plus cosine squared, this is called the Pythagorean identity. You're going to be able to change, anytime you see sine, you love sine squared plus cosine squared, because you can just cross it out and put 1. Okay, that's called the Pythagorean identity, because it came from the Pythagorean theorem. Okay, so we'll be looking for that. Okay? Okay, we'll see if you know your algebra now. Here's the algebra simplification part. Okay, now there's a whole lot of steps in algebra. Let's break it up into, let's start with multiplying and factoring. Okay? And typically in every one of these problems, it's somewhere along the way, if you don't have everything in terms of sine and cosine, we're going to want to change them into sine and cosine, using the things I just showed you. Okay, and I'll help you out. I'll give you a bunch of examples. Okay? Let's look at example 1. Well, let's see. The cosine of the tangent, the cosine times tangent times, okay? Well, let's start off looking at the tangent and the, so I'm going to multiply out. Okay, multiply the cosine times the tangent and the cosine times the secant. I'm distributing. Okay? Now the tangent is the same as sine over cosine. We just showed you that. And the secant is the same as 1 over cosine. This is going to make life much easier, because in this term here, if you look, I can cancel. And in this term here, I can cancel. And what do I end up with? Sine of y minus 1. And that's your answer. That's what we mean by simplifying, basically turning everything into a sine and cosine and canceling out as much as I can. It's breakfast. It's easy. Okay? Okay, let's try another one. But the point of that one was to change everything into sine and cosine if you can. Okay? Okay. The next ones are going to involve greatest common factors. Before we show you it with sine and cosine, let me show you it with algebra, just in case you forgot. Okay? What's the greatest common factor of these two numbers? Ooh, I forgot. Okay? Well, to do this, we're going to factor them. We're going to break them up as far as it'll go. Let's see. 45 breaks up into 5, 9. 9 breaks up further. Okay, 3 and 3. A to the 4th, we'll break that in. Oh, that's 4 A's. B to the 2nd breaks up into 2 B's. Okay, so basically the end points of this whole thing is this. Okay? Okay? Let's break the other one up as far as he'll go. 2 and 9. 9 breaks up further. 3 and 3. And the A is just A, and the B will break up. Now, so the end points of this thing, as you can see, are in the circle. Now, what I'm looking for in the greatest common factor is what's in both of those groups. What's in both of those groups? Common to both of those groups. Well, I see there's a 3. There's 2 3's in both of them. Okay? There's an A. There's 1 A in both of them. There's 4 in the other, but it has to be in both. Okay? And there's 2 B's in both of them. So my greatest common factor in this case is going to be what's in both is the 2 3's, the A, and the 2 B's. And the answer, in this case, the greatest common factor is what's in both is 9AB squared. Okay? Why do we need that? Because in the future, we're going to have to factor out the greatest common factor. Let's do another problem. How about this one? Okay? We'll find the greatest common factor. In this case, it's 3xy. It's the number that goes into all 3 of them. Can't go into 2 out of the 3. It goes into all 3. Okay? And now I'll take him out. I'll factor him out. Remember this? I hope so. Okay? If I divide that, let's see, 21 divided by 3, x squared divided by x, y divided by y, I get 7x. And this is what I mean by taking it out. Do your division here. I get minus 2y. Okay, the x's just canceled out. Do your division here. Got to do it to everybody or nobody. Okay? And now what happens when everything cancels out? You get 1. Okay? How do you know you're right here? Okay? How do you know you're right? Well, let's check it. Let's multiply out. U times U, I got it. U times U, you got it. And U times U. Now, if you don't get it, you know you're wrong. Okay? So that is the answer. That's why we need the GCF, the greatest common factor. Okay? Ha-cha-cha. Okay, well, now let's look at this in terms of trigonometry. Okay, factor and ugh. Okay, what would the greatest common factor, what goes in to both this term and this term? Okay, this is the same stuff you did in algebra, don't get afraid. Well, it's going to be the cosine squared. Okay, I see a cosine squared in here, and I see a cosine squared in here. That's the most that goes into both. If I factor him out, uh-oh, look what I have in parentheses. I love that. You love sine squared plus cosine squared, because by the Pythagorean identity, remember, it's 1. So the point of this problem is always be looking for sine squared of anything. Sine squared hooga chugga plus cosine squared of hooga chugga, I don't care what it is 1. Okay? And you can cancel it out, and that's some great simplification there. Okay? So that's a factoring example, and you'll have one in the homework. Okay? Okay, what about working with fractions? Ugh. Remember this? You were allergic to it? Chapter 6, I think, of algebra. Okay? Let's see. Oh, gosh, I hate this. Complex fractions. What was the trick for complex fractions? The trick was multiply everything by the least common denominator. Okay? Let's see. If I multiply by 1, the way he dresses up on Friday night as LCD over 1 over LCD over 1, I haven't broken any rules if I do that. Okay? And that's what we're going to do. Let's see. What's the least common denominator in this case? It's xy, right? I'm going to multiply everybody by xy. xy over 1, xy over 1, everybody gets them, all 3 in this case. Okay? If I do that, in the top, let's see, I'll get 5xy. Okay? In the bottom, I can cancel those x's, and I get a y. That's good. No fraction. I like that. Okay? And in the bottom, I can cancel the y's, and I get an x. Okay? And that basically simplified the complex fraction. Okay? That's the trick, the LCD over 1 deal. Okay? Now, don't even think about doing that. You cannot cancel things that are added. Remember that? That's a very common mistake on students' parts. Okay? The reason you can't do it is because canceling is division. Okay? And if I look at this, division can only undo multiplication. You can't undo addition with division. Okay? So don't even think about doing that. Okay? Remember that death will come to those that cancel things that are added. Okay? Okay, well, let's go back. Let's do a similar animal with trigonometry. Okay, let's look at this bad boy. Holy, go to war. That doesn't look too bad, except, remember my deal was change everything into sines and cosines, etc. Well, let's see. The cotangent of a negative angle is the same as the cosine over the sine. Remember that? The cotangent, we could simplify that. And the cosecant, what was that in terms of sine and cosine? 1 over the sine. Okay? So now I got everything in terms of sine and cosine. Okay? Now, what do we do with complex fractions? We use LCD man. LCD man. Okay? And I'm going to multiply by the least common denominator of everybody, sine of the negative angle. Okay? Which isn't cheating because it's 1. So anything over itself is 1. Okay? There I get a nice cancel. And what is this going to equal? In the top, I'm going to have cosine of negative, and in the bottom, everything cancels, so I get a 1. Okay? Not too bad, except there's more you can do, because remember the rules of negative angles. The cosine of a negative angle, remember the cosine involved the x in the 4th quadrant there. What can we do with that negative with a cosine? You can just take them away. Okay? Couldn't do that with the sine, but you can do it with the cosine. Okay? So that's your answer. And that really, you needed to know all of algebra and a lot of trigonometry to simplify that nightmare. Okay? A little bit of review. Let's look at another one. That's complex fractions. LCD man involved. LCD over 1. That's what we're trying to review there. Okay? Okay, let's do some canceling. Okay, ugh. What do we need to know not to do? Don't do that. Okay? Don't even think about it. You cannot cancel things that are added. Okay, it's the most common mistake. What do you have to do? Oh, the reason, because it wouldn't be division by 1. okay? You cannot subtract something from the top and bottom. Okay, you can divide something by the top and bottom, but you can't subtract something from the top and bottom. Okay, what we need to do is bring out Factor Boy, because Factor Boy is going to allow us to divide. Let's factor. Let's see, we factor the top. We're going to take out a common term here. Take out 2x. It didn't help me much. Well, let's factor the bottom. Factoring, I'm not going to review factoring, okay? Factoring, that factors into 2x plus 1 and x plus 3. Now, I love this factoring because now what can I do but cancel them? How come I can cancel those? Because they are multiplied. Okay, it's perfectly legal to divide by 1. Okay, and I'm seeing 1 as x plus 3 over x plus 3. See it? There's a 1. That's how he dresses up in the Easter parade. Okay, so I can do that, and it cancels. Okay, can you do this? I say this over and over again. People still do it. No, you can't. So this is your answer. Okay, that's it simplified. Let's look at it as far as trigonometry. Okay. Holy go to war. Look at this bad boy. Show this one to your mom. Can we cancel these? You knew you couldn't. Okay, so what do we have to do? Hello, Factor Boy. We have to factor out, what's the common term? Let's factor the top. I notice I can factor out a sign, and in the bottom I can factor out a sign. And if I cancel, what do I get? And I could try to change that tangent into sine over cosine, but I think we're going to live with this at this point because it does demonstrate the idea of factoring before you cancel. Okay? Remember, you have no legal right to subtract something from the top and bottom. You have to factor before you cancel. Okay? Remember how to multiply fractions. They're going to give you some of these. Okay? Basically, what I do is multiply the tops and multiply the bottoms, but then I'll get high numbers. Okay? So rather than I'm allowed to do that, but rather than doing that first, what I'm going to do is cancel first so that I don't get the high numbers. It's either multiply and then cancel or cancel and then multiply. Let's do it. Okay? Let's see, what cancels? The y and the y squared cancel, leaving me with a y in the bottom. The x's are gone. They're out of there. Okay? What else? And that's it. So I just multiply what's left. 3 and 7, and y and 4. I usually put my number first. And that's my answer. Okay? I think the trick in this one is to multiply first. I'm sorry, cancel first, then multiply. Then you get less high numbers. Okay? What's the difference between that and division? Okay, well, division's the same thing. It's simple, except with division, you multiply by the reciprocal of the second fraction. So if you know how to multiply, all you have to do is reciprocate the second fraction, and that's how you divide. Okay, so we're going to multiply, but remember, before we multiply, we want to cancel. Okay? Now, what's left? I don't see any more canceling, and I get 7/4. Okay? Well, it's the same deal with trigonometry. Okay? Oh my gosh, look at this bad boy. Okay? We want to divide that. Well, that's going to be the same as, looks hard, but it's not hard at all. This is one of the easier ones. The first fraction times the reciprocal, the bottom goes to the top goes to the bottom, of the second fraction. Okay? Now this turns out not being so bad, and that's what we're testing you on to see if you know division. Okay? They're reviewing algebra here. Okay? Can we cancel anything? Always cancel before we even think about multiplying. The secants, they're out of here. Okay? And I see some cross-canceling with the tangent squared, and the tangent to the third, if I do it, that's going to leave me with just one tangent, or tangent to the 1th in the bottom. Now what's left? Okay? Well, if I look up at the top, nothing. Okay? If I look at the bottom, I have a 3 and a tangent. But you can't write the answer this way. Okay? You can't write the answer this way because you have to have a top. You don't have to have a bottom, but you do have to have a top. Remember the number, for instance, 5 over, or 5. okay? Could be written as 5 over 1, okay? So whether you have it 5 or 5 over 1, you don't have to have a bottom, but you do have to have a top, okay, if you have a fraction. So what we're going to do is make a top. We're going to make a top. We're going to make it a 1. Okay, you can throw a 1 around like it's, you know, nothing. Okay, so that's the deal in this case. 1 over 3 tangent x. Okay? Okay, let's see. We need to find the least common denominator. We need to review how to find the least common denominator of this and this. How do I do that? Well, let's break them up. Okay, break them up, or known downtown as factoring. We'll break them up as far as they'll go. This breaks up into x squared and y, and the x squared can be broken up further. We're going to take it as far as it'll go. Okay, x and x. So I have a set of 2 x's and a y. Okay, remember this? Okay, now, the least common denominator of these two, I'm going to have to break up y to the third x. It's going to break up into those two, and one can be broken further. Now I have a set. Now what I want to do here is construct a term down here, it's the least common denominator, that contains both of these, this and this. Okay? I got to make sure that everything's there. Okay? I need to make sure an x is there. I'll put it. Make sure this guy's there. I'll put it. Make sure this guy's there. Okay, so this first set is covered. Okay? Now, what about this guy? Well, he's already there. So I'm hunky-dinky. Okay? What about this guy? Well, I already have 1, but I don't have 2. So I'm going to add 1. And this guy, I'm going to add another one, because I have to have 3 y's. I have to have everything covered. And this guy, this x, is already covered. Okay, I have 1x. Okay? So basically, I have everything from both sets. So that's my least common denominator, x squared y to the third. Let's check it. Is everything in x squared y there? I can see that it is. Okay? Is everything from y to the third x there? It's in there. It's kind of an overlap, but it is in there. And that's the idea. I'm looking for the smallest number that contains both of them. Okay, so that's kind of the construction of a least common denominator. Remember that I had to break everything up first. So that'll do it. That's the least common denominator. Well, it gets a little bit harder. How about the least common denominator of this? X squared plus 5x plus 6. And 5x squared plus 15x. Eee. Well, just like we broke up those previous ones, we're going to break these up and factor them. Okay? The first one, x squared plus 5x plus 6, if I factor it, it's a basic factor, it's x plus 3 and x plus 2. And I can't break those up anymore, so that's it. Okay? The other one, I don't think it's a 2 parentheses deal. I think there's a common term I can take out. What comes out of both 5x squared and 15x? I smell 5x. And 5x comes out of that. So 5x times x is 5x squared. 5x times 3 is 15x. Okay. Now I've got to construct this thing so that everything's in there. I need an x plus 3. I need an x plus 2. Okay? That takes care of everybody over here. I need a 5x, and I'll throw him in there. I need an x plus 3, but he's already there. So I'm not going to add another one. I would add another one if I needed 2 of them, but I don't. Okay? I like to see, let me check it. I can see that everybody's covered here. And I can see everybody's covered there. There's the x plus 2 and the 5x. So believe it or not, the least common denominator of these is this nightmare. And I'm not going to multiply it out. In fact, it's easier to manipulate leaving it like that. Okay? So that's basically the way of finding a least common denominator. Why do we need to know how to find a least common denominator? Well, that's how we're going to add fractions. Okay? That's our next review, adding fractions. If we look at this example, we're supposed to add this to this. Whew. Well, you can't add fractions with unlike denominators. So I'm going to get a common denominator. Okay? What is the least common denominator in this case? Okay, well, I'm hoping you could find it from our last example. And we'll say that it's 15x squared y. Okay? And we put it on both. It is common. I'm going to put it on both. And I'm going to create two equivalent fractions that have the same bottom, the same denominator. Noticing that I multiplied the bottom by 5y here, I can't cheat. I have to, the 2's saying, what am I, dog meat? Got to multiply him by it as well. And that'll give me a 10y here, and an equivalent fraction. That's not cheating, because I multiplied by 1. Okay? The bottom, I notice I multiplied by 3x squared. So I better do it to the top, or x is going to be pretty mad. Okay, and what do I get? 3x to the third. Once again, as you can see, I didn't cheat. I multiplied by 1. That's why I need this least common denominator. Well, now I have two fractions that I know how to add because they have the same denominator. And all I do is add the numerator of this one to the numerator of this one, and I get 10y plus 3x to the third over 15x squared y. And that's the deal. Okay, so that's the basic idea of how to add fractions. Okay, how are we going to do this with trigonometry functions? Ooh, this is a hard one. Okay, let's take a look. This is a subtraction. It's the same, except you subtract instead of add. I'm going to write, a lot of times I write it like this because in the book they have them sideways, but you know you're going to have to put one on top of the other. Okay, so as soon as you see an addition or subtraction of fractions, do that. Okay, we need a least common denominator in this case, and it's a buzzy bear. Okay, I don't see anything that both of these go into easily. So you know what I do? Sometimes you just write them both. Sometimes you have to do that. Okay, that's all you can do. Now I say, what did I multiply this by to get this? Okay, all right. What jumped in from here over to this whole thing is the sine x plus 2 plus cosine x. So I multiplied the 2 by that as well. Okay? Now what jumped in to go from here over to here? Well, what jumped in? Here's the sine x plus cosine x. Well, the new thing is the sine x minus cosine x. So I'm going to have to multiply 3, or I should say I should multiply negative 3 by that. Okay? Now if I multiply everybody out, 2 times him, 2 times cosine, minus 3 times him, minus 3 times minus cosine, what will I get? Ugh, look at all that, okay? And you can multiply it all out, and I have 2 of these, and minus 3 of these, etc., and it'll come out to minus 1 sine and 5 cosines. I think that the second part is easy. It's the getting the least common denominator part for fractions that's tough, okay? And that's, we'll live with that, okay? That's a decent enough answer. Okay, that's just a little review of adding and subtracting fractions. It's the same thing with trigonometry functions as it is with anything else. Okay? Okay, what about radicals? Ooh, radicals. Remember these? Let's see. If I asked you to multiply and simplify these two radicals, okay, remember radicals, you can just multiply radicals times radicals. Okay? I'm going to get 45. Square root of 45. Okay, but that's multiplying it. Now it asks you to simplify it. Remember, simplifying, we want to take out as much exactness as we can, as much perfect square root as we can. So we'll always at least look to break it into, simplify it. We'll look to break it into what I call the good, or the perfect squares, and the bad, which is what's left over after you do that. Now what's the biggest perfect square that goes into 45? Well, 9. And then what's left over when you multiply? Well, 5. Okay? Now, once I've broken it up into what I call good and evil, the square root of 9, why is it good? Because I know what it is. It's 3. Okay? The square root of 5, why is it bad? Because I can't do anything with it. So don't. And that's the, after multiplying, that's the simplification. That's your answer. That's all you can do. Okay? You've taken out as much exactness as possible. Well, let's review variables with this. Okay? How about this bad boy? Holy, go to war. Look at that. Don't be afraid. It's not that bad. Okay? We'll break it into good and evil. Let's take it one thing at a time. Okay? What's the biggest, the largest good square, if you would, good square root that goes into 50? 25. It's going to help you to get to know the perfect square roots. Okay? I hope you still know them. And what's left over from that is 2. Now, what's the largest perfect square root that goes into x to the third? Well, That's x to the second. Okay, and what's left over after you take x to the second out is just x. Okay, now we're taking it one thing at a time. It's not that hard. What's the largest perfect square that goes into a to the sixth? Keeping in mind that when you multiply exponents, you add them. Okay, a lot of people would think a to the fourth, but actually, the largest perfect square in this case is a to the sixth. Sometimes the whole thing is good. Okay, a to the sixth is a perfect square root. Remember what the square root of a to the sixth is? A to the third. Okay? Okay, so there's no leftover. Let's look at b. Sometimes they're all bad. Okay, b is, there's no goodness in b, if you would. No perfect square root in b, so we just put him over in the leftover pile. Okay? Now the reason this first part is good is because we can take the square root of it. What is the square root of 25x squared a to the sixth? Okay, there you go. And the reason this part is bad is because there's nothing I can do with it, so I just don't do anything. Okay, so that's simplifying. Let's do it, of course, with trigonometry. Ugh. Let's put them together. Let's put them together into one. Oh, I'm going to. First thing I did was change the tangent into. Oh, that's good. Change the tangent into the sine over the cosine, which leads me to believe I'm going to change the cotangent. Remember what the cotangent is? It's the cosine over the sine. Okay. Now, hopefully, if I put them all together, I'm going to get some canceling. Okay, and then we'll simplify. Let's see. What can I cancel? Those go away. Those go away. And what am I left with here? I got a sine to the 1th and a sine to the 2th. That makes sine to the 3rd power. And I'm going to break him up, just like I did in the previous slide, into good and evil. Okay, what's the largest perfect square that goes into sine to the 3rd? Sine to the 2nd. I know, it's easy. I know what the square root of that is. Okay, and what's left over from that? Well, let's see. The sine. Okay, so the reason that sine to the 2nd is a perfect square is because I know what the answer is. It's sine. Okay, and the reason the square root there of sine to the y is left over is because I don't know what to do with it. And that's as simple as you can make this. Think of that, man. You took all this garbage, and turned it into this. That's a lot better. Okay, and what we were testing you on there is to see if you can simplify radicals. Okay, it really doesn't have that much to do with trigonometry if you think about it. They're trying to review your algebra. Okay? Okay, let's look at some more. Trying to review that the tangent is the sine over the cosine. We're trying to review that the cotangent is the cosine over the sine. And we're trying to review the idea of breaking it into perfect squares and the leftovers. Okay? That's why we're making you do all this. Okay? Okay, what about another thing we had to do back in algebra class was rationalize the denominator. You weren't allowed to have a radical in the denominator. Okay? Now, that means that the square root of 7 was the troublemaker. Whoever the troublemaker is, that's what we're going to get rid of. And the trick for getting rid of this was to do something legal. You have to do something. You can't be just doing crazy things. Was to multiply by the square root, whatever the troublemaker is, multiply the top and bottom by it. Now, that's legal because you're really multiplying by 1. Right? Okay, and what happened? And they promised it. If you did that, it would simplify. Well, let's see. It's going to simplify to multiplying the top by square root of 7 over square root of 7. 2 radical 7, and that doesn't look any better, but because you're allowed to have a radical in the top. It's the bottom that's the troublemaker. And multiplying the bottom, we get square root of 49. Well, that doesn't look any better, except that that'll always be, if you pull this trick, it'll always be a perfect square. Thereby, you won't have a radical in the bottom. You might have it in the top, but you're allowed to have it in the top. Okay? So that's our answer there. Well, you can have radicals in the numerator. Okay? Well, here's another one with, let's take that same concept and change it into trigonometry. Okay? Let's see. Ooh. The square root of the sine over the cotangent. Okay, well, let's see. That's going to be the sine of y over 1 over the cotangent. Okay? Well, wait a minute. What is 1 over the cotangent? What is the reciprocal? Remember I told you, we always want to try and change these things into sines or cosines or tangents or something. Okay? Well, that's the tangent. Okay, well, we're getting there. We're getting there. Okay. What is the tangent? The tangent is the sine over the cosine. Okay, so now we're getting there. Let's multiply everything out, and we get the sine times the sine. We get sine squared over cosine of y. Well, let's see. Who's the troublemaker here? Cosine of y. We're not allowed to have a radical in the bottom. So what was the trick? Multiply the top and bottom of the fraction by that, which is what I'll do. Okay? Which will give me in the top the square root of sine squared cosine, and in the bottom, cosine squared. Doesn't look that much better, but the bottom will be a perfect square. Okay? Let's see. Let's break it into perfect squares. Oh, this I'm going to do. I'm going to keep it as one giant fraction. I'm going to break it into perfect squares, which is this. That's all perfect. Okay? Times the leftovers, which is this. Okay? Now my perfect guys are perfect, so I can take the square root, and I've simplified it. I don't have any radicals in the bottom. I'm good to go. So that's my answer. Okay? So what we're looking at here is reviewing, rationalizing. Well, first of all, we're looking at that 1 over the cotangent is the tangent. We're looking at the tangent is the sine over the cosine. And we're looking at our trick for rationalizing, and that is to multiply the top and bottom by whatever the troublemaker is. And the troublemaker, remember, is the radical that's in the bottom. Okay? Okay, let's just do a couple more simplifications. These are some of the harder ones that were similar to the ones in the homework. Okay? Holy, go to war, Miss Agnes. Now, this one I screwed up on. I want to take you through my screw-up, so hopefully you won't make this screw-up. Okay, the first thing I thought of, well, I got a bunch of things that aren't sines and cosines here. So let me try and change them into sines and cosines, okay? Well, let's see. The cosecant, how do we change that into something of a sine? And the tangent, I want to change that, okay? Well, the cosecant, okay, you remember the cosecant is 1 over the sine, okay? That's going to help simplify things. And the tangent is the sine over the cosine, okay? Now looking at this, let's see. If I multiply that out, that's going to come out real nice, okay? And if I multiply that out, well, it's a mess, but I think I'm going to have some canceling involved here. Let's see. That will cancel, and I'm left with a sine. This is going to cancel like there's no tomorrow. That's going to be cosine, and that's going to cancel, and I get cosine. And the bottom is sine x over plus cosine x. And if you look at, you got the same thing in the top as you have in the bottom, which means this thing has got anything over itself is 1. So this, I know when you get 1 as an answer, you know you're right, okay? And that'll do me for that one, okay? Let's look at one more. Can you hang in there with me? This is the one I screwed up. I would think of another one. This is the one I tried to change into all sines and cosines right from the get-go, which doesn't always work. Okay, sometimes you have to wait a little bit. Okay, let's try it. The cosecant to the 4th power is the same as 1 over the sine. Remember, the cosecant is 1 over the sine. Okay? Then I'm going to once again change the cosecant to 1 over the sine, and the cotangent, I'm not going to change it into the tangent. I'm going to change it into the cosine over the sine. Okay, and once the same thing, I'm going to change it into the cosine over the sine, which distributes the 4 as an exponent. Well, looking at this, I'm not seeing anything helping me out here. Okay, so sometimes you have to back up and say, I guess I screwed up. Okay, and I'll just revisit it again and say, maybe there's another way. Maybe I'll wait, look at it again, and not change things into sine and cosine just yet. Okay, let's take a look. Well, if I remember factoring, okay, I can factor this thing with 2 parentheses. Okay, and remember that the first 2 always gave me this guy, and the second 2 always gave me this guy. Okay? Well, that would give me the first guy. And that would give me the second guy. So I'm starting to get close to factoring here, okay? Now I need this and this to add up to minus 2 cosine cotangent. So I think the plus and plus is not going to make it, okay? I think I need minus and minus, yeah. And if you check your factoring, that's going to work. Okay, now how did that help me? Well, you never know. Let's try now changing it into sine and cosine, okay? Well, the cosecant, what is the cosecant? Remember, it's 1 over the sine. So cosecant squared would be 1 over the sine squared, okay? Minus the cotangent squared, which is the cotangent is the cosine over the sine. Remember, these are things worthy of learning, okay? So if it's cotangent squared, it's going to be cosine squared over sine squared, okay? Now cosecant squared, we're back to cosecant being 1 over the sine, so cosecant squared will be 1 over sine squared, and cotangent squared, we're back to cosine squared over sine squared, okay? Well, how's this going to help me? Well, wait a minute, I have two fractions here that have the same bottom. Both of them have sine squared. Oh, over here I have two that have the same bottom. Okay, I think I have a break here. Okay, so I could say this is 1 minus cosine squared over sine squared, just putting the two together because they have a similar denominator. And over here, these two have a similar denominator. Okay, I'm getting there. Now, let's see. 1 minus cosine squared. Well, I want you to think about this. This is probably the hardest one. That's why I'm going over it. Okay, 1 minus cosine squared. What do we know about sine squared plus cosine squared? Sine squared plus cosine squared is 1. Remember by the Pythagorean identity, sine squared plus cosine squared. So if sine squared plus cosine squared is 1, what is 1 minus cosine squared? Well, if you take cosine squared away from 1, you'll get sine squared. Okay, let's do it. We'll take cosine squared away from 1. Remember? Take this away from 1. Guess what we're left with? Sine squared. Now so this whole top is equal to sine squared over the sine squared. You love that. And this whole top is equal to sine squared over the sine squared. You love that because guess what this is? This is 1, and guess what this is? This is 1. Holy, go to war. All this stuff came out to 1. Okay, what a nightmare. What were we checking on to see if you knew the cosecant was 1 over the sine? Okay, the cotangent was the cosine over the sine. That you could factor, all these things. Okay? Okay, well you might say, I already knew all that. Well, that's fine, but that's your review. Okay? So guess what? It's homework time. Go do homework number 8. It's listed in the syllabus. And if you have any questions, by all means, let me know. Either email me through the homepage, www.mc.cc.md.us/Witte, or call me. Otherwise, we'll see you next time. And don't forget, do your homework. You can't survive if you don't do your homework. See you next time.